Good morning, everyone. Thank you so much for coming. It's wonderful that you're tuning in and that you're interested in what we are doing here. And before I start, I'm sorry for my voice, and I'm sorry if I start sneezing in the middle because we are in a flu season here. So this is not me exactly. But I will try to still. I mean, yeah, I'm really super happy actually to moderate this and I will try to be on top of my game as much as I can. So today we are going to speak about the modeling approaches and solutions and results that we are having in two projects for the modeling for the sandfly-borne diseases. And I have to say that I'm really, really super happy to be moderating this first because this is a first joint effort of two projects, CLIMOS and Planet4health, and I hope that it's not going to be the last. And I have to say thank you, F6S, for organizing us because F6S is our partner in both projects in communications of the projects, and they're doing really, really wonderful job. And one of the results of their wonderful job is this seminar. The other thing that I'm absolutely grateful for is that I'm moderating the seminar about data analysis and modeling for One Health and Planetary Health, which is something that I'm really interested about and I'm also working on. And in this case, we are going, as I said, to show you how we got from data that we have to the modeling results that we have. And then next webinar is going to show you our output, the early warning systems on the two projects for the sandfly-borne diseases. So before I give the floor to the speakers, I just want to tell you a bit more about the data. So in the CLIMOS project, CLIMOS project is now has entered the fourth year of the project realization, is going to end in May this year. And we have managed to reconstruct and to generate a really large sandfly surveillance historical data set, and then also the data set that was made during the project. And during the project, we have produced more than 7,000 new data points, which means new trapping events that were done over the 2 years of monitoring in 12 countries in Europe, in Turkey, and in Israel. And you can see in this map where the trapping locations were in Project CLIMOS. And aside from these large amounts of data on sandfly surveillance from sandfly monitoring, we also in the Project CLIMOS have the pathogen data set that has information about the Leishmaniasis toscana and Sicilian flaviviruses cases, the infections both in sandflies and then in humans, and then dog sera data, human health data, climate and bioclimatic variables. Then we have our customized soil moisture data set and then socioeconomic data sets. And in Project Planet4health, which is also dealing with sandfly-borne diseases, but just on the Iberian Peninsula, we are focusing on the dog health in the sandfly-borne diseases context. And then here we have additional data sets of the sick dogs and then of the dog diagnostic serological tests as a proxy records for sick dogs. And we have a really, really good and big data sets from around more than 1,000 locations in Spain and 450 locations in Portugal. And aside from that, we also are using mosquito alert data. Mosquito alert is a large citizen science repository of mosquito information. And we are also doing cross-species modeling, which we are not going to speak about here, but anyways, just for you to know. And so our speakers today, which are not going to go in this order, but they're going to be in the order. So it's going to be Yoni Waitz and then Sergio Natal and then Danyang Wang are going to tell you more about how we use these data sets, these really wonderful data sets, to try to better understand and then forecast the risk of sandflies specifically, because this is what we are going to speak today about sandflies presence or abundance in Europe, Turkey, and Israel. So I will give the floor to Yoni Waitz. He's coming from University of Haifa, and he will take on from here. Thank you so much.
Okay. Hmm. Okay, can you see my screen now?
Yes.
All right. So thank you, Suzana and Sandra, for the invitation and introduction. What I'm going to do now is basically a lineup introduction about sandflies and modeling in general. And later on, my colleagues will introduce you to the modeling, the core of the modeling itself. So I will start with the title of the project, and as you can see, that one of the words is detection, and by that it means that is the basic concept of what models might do, which means um, detect the abundance and distribution of sandflies. And in fact, one of the tools that this project will provide, and I won't talk much about it because it's going to be the next webinar, it's the early warning system, which is a database tool in order to um, uh, predict and make a warning about sandflies occurrence and expansion in short and large long term. And I will go directly to this basically the question of what is the type of models that we are using. So in general, models are tools that start with a question, look for a way to approach it, and then try to validate it. Those are empirical models. And our models based on historical observations on both sandflies and environmental data. And basically, those are spatial models. So in fact, one of the most crucial and important issues that we need to take care of when we are working with spatial data is that the scale matters. And there is a trade-off between the amount of data that we can obtain and the amount of work that we can do, and the resolution that the model can work on. And later on, the meaning of the model is driven by the scale of it. So let's dive into the world of Sandfly. So if there are some people here who haven't been in any of the previous webinars or never met Sandfly, so it's a very diverse and large group that covers most of the world. In our case, we are interested in two specific genera. One of the genus is Phlebotomus, which is common in the Old World, meaning Europe, Africa, and Asia. In the New World, in Americas, we have Lutzomia. Both of them are the main vectors of Leishmania parasites. We're talking about approximately 20 species of Leishmania pathogens, and that are being carried with approximately 100 vectors that known so far, and something about around 1.5 to 2 million cases for leishmaniasis each year. And if we are doing zoom in to our region of interest, which is the Mediterranean and Northern Europe, this map can show you the coverage, the extent of the sandflies that transmit one of the forms of Leishmania, which is Leishmania infantum, and the distribution of the species. And based on the expectations of climate change, it might climb northward. And for those of you who didn't never met the cycle of leishmaniasis, basically there are three partners in this cycle: the vectors, which are the sandflies, the parasites, and the host reservoirs that might be asymptomatic or symptomatic. They can be humans, wild or domestic animals. And the disease can be in one of the three forms: skin cancer, which is the cutaneous leishmaniasis, mucocutaneous. I didn't bring any example for it. And also visceral leishmaniasis, which is an internal disease of the organs. And beside that, also there are many viruses that can also be transmitted. And I also will mention the cycle of the reproduction, the biological cycle of sandflies. As many other insects, they are temperature sensitive, and therefore climate change also will cause changes of the rate of their development, and will affect the population size. So how do we know what we know about sandflies? This all starts in field collection. Suzana mentioned the amount of fieldwork that was during the project. This is just one example of the study sites from Israel. In the desert, you can see that one simple CDC trap can provide thousands of individuals that need to be mounted and then checked beneath a microscope according to taxonomical identification. It's a lot of work, and eventually all of this work, this one trap is just one observation in space and time. And eventually we need to use the models as an interpolation method from the point into a grid, into something is in a larger scale, and that is a challenge. And I want to give just another one example of how this simplification is a challenge and affects the way we can ask questions. This is the work of Cristiana Kazan in northeast Romania, the northern border, I might say, of Phlebotomus perfilievi, which is one of the species that we work in, is mostly common in the eastern part of Europe and like in our extent. And as you can see that this work was focusing on one farm, and it has a lot of traps around the farm, and it caught, like you can see in the illustration on the left, only the traps that were next to the poultry barn. The chickens were positive, meaning it's highly focal. It's focused, their abundance, their presence. It's only next to this specific location, and also the seasonal pattern, and you can see in the graph below, is very narrow. It starts in July and ends in August, meaning you have a very short window to catch the entire activity season. And it makes sense because it's the northern region, it's pretty cold most of the year. And if you would ask yourself whether there is any connection between the sandflies and the chicken, probably not. The assumption is that this abundance, this focal abundance, is only mostly related to the material that used to build the shelters of the chicken, which is clay and wood, and nothing about the chickens. So regardless about this specific question, it's just an example of how the specific local condition affect the distribution and abundance And eventually, we want to go to this larger scale of the entire region, and therefore, the way we ask questions are related to the scale. And from that point, I will leave the stage to my partners who will say something about the models themselves. Thank you.
Thank you, Yoni. So Yoni just introduced us to the small part of the complication of modeling for the sandflies. Thank you, Yoni, for that. And then I'll give the floor to Sergio and then to Danyang. And they will actually both speak about the machine learning solutions for the modeling for the sandflies. Sergio will speak about modeling for the presence, absence, and the abundance of the sandflies. And Sergio is coming from the Spanish SME called Predictia. And Sergio, please, the floor is yours.
Yes, thank you, Suzana. Do you see my screen?
Yes.
Okay. So thanks for the introduction, Suzana. Now I'm going to present our climate projection approach based on machine learning. This work focuses on understanding how climate drives sunfly distribution and how this distribution may change in the future under different emission scenarios. So the goal of this approach is not only to model presence and absence, but to understand how climate change can reshape risk patterns over time. So the main objectives of this approach are to develop machine learning models that explain the presence and absence of different sandfly species, and to project these results into the future under different climate scenarios. This allows us to assess how their spatial and temporal distribution may change and how, as I mentioned before, how risk patterns may evolve in the coming decades. So first of all, I'm going to talk about the data that we have been using to develop this kind of models. So the first one will be our target dataset, or Sandfly dataset. Is organized by species and carefully pre-processed. So we clean the data, harmonize species name, and combine information by sex to improve our data density. For this approach, we also introduce synthetic absence in the boreal regions in the north of Europe, based on ecological knowledge and published literature to correct the sampling bias. This is important because the field surveys are not randomly distributed, but they are just focused on known present areas. I mean, people who cares about to go to the field, they tend to go to that points or that locations where they can find sandflies. So it's for this modeling task, it's important to introduce some zeros. For the predictors or features that we use to train the models, we use bioclimatic indexes from ERA5 land reanalysis data produced by Copernicus. These variables represent temperature, precipitation, seasonality, and climatic extremes, as well as dew point temperature and altitude. Together, they provide, let's say, coherent climatic description of the environmental conditions that shape sandfly ecological niche. As expected, many of these variables are strongly correlated. If we check the figure on on the right, meaning that they contain redundant climate information. This reflects the natural structure of climate systems, but it also creates a challenge for modeling. For this reason, feature selection and model regularization are essential to avoid overfitting problems and improve the interpretability of the models. So, as I mentioned at the beginning, our modeling objective is to predict presence and absence using climate-related variables and machine learning models. So, at the beginning, during this task, we test different machine learning techniques, from the simplest one to the hardest one. So we use decision trees as a simple and interpretable baseline. We also use random forest as a robust ensemble method, and XGBoost as a regularized boosting approach that performs really well with small data sets, as we are working with. And this type of techniques based on boosting allows us to avoid the overfitting of the models and create that balance between interpretability and overfitting. Here we can see the main workflow to develop this model. So we follow a species-specific modeling strategy where each species is modeled independently. I mean, we separate the species. We have one model per species. And this framework follows a data-driven approach, meaning that the models learn patterns directly from the data, using climate variables and observed Sandfly presence. We also perform global hyperparameter tuning across the species to ensure computational efficiency and model stability. Then we train species-specific models, select the best performing model for each species, and apply a feature selection to reduce that type of redundancy that I mentioned in the third slide when I talk about the features that we are using. And finally, this workflow, this approach, produce and optimize and interpretable models that are ready for the future climate projections. For the future projections, we use Eurocordex, which is a regional climate simulations with a spatial resolution around 9 kilometers. We consider historical conditions and different emission scenarios, including RCP 2.6, RCP 4.5, and RCP 8.5. We also use multimodal ensembles to increase the robustness and reduce dependence on individual climate models. For in the next slides, I will show you some results for different species, and these results are aggregated and visualized at NUTS 3 level. We thought at the beginning, when we start with this type of modeling, that this scale is a good compromise between spatial detail and robustness, and it is also most useful scale for this decision making, public health planning, and risk management, because it matches the level at which which many surveillance and management actions are organized. We thought that it's easier to make some decisions or some approaches if we check these results at NUTS 3 level. Here we can see three different panels. The first two panels are from the results from our models, and the third panel is a comparison with the existing literature. So when we compare our projections with published studies, we observe very similar spatial patterns and expansion signals. This structural consistency with the literature gives confidence that our modeling framework is capturing the main climate-driven process that shaped Sandfly distribution. For the species shown here, the projection indicate a clear northward expansion of climatic suitability. Under high emission scenarios, the second panel, suitable conditions progressively extend into Central and Northern Europe. This reflects a climate-driven redistribution of ecological needs, mainly controlled by temperature and seasonal constraints. And these maps and, let's say, animations show the temporal evolution of suitability over time. We observe stable core areas together with expanding margins. This indicates that climate change is not creating random patterns, but structure and progressive shifts in suitability. These results show that future change in Sandfly distribution are climate-driven, scenario-dependent, and especially structure. The projections suggest a redistribution of risk rather than an uniform expansion, with clear gradients and directional shifts driven by long-term climate change. From a public health and risk perspective, this implies the emergence of new risk areas, changing exposure patterns, and the need for anticipatory surveillance and planning. So climate-driven redistribution of vectors directly translate into changing disease risk landscapes. I think that that's all for now for this approach, and I would like to give the floor to my colleague Danyang, that she's going to introduce another approach to produce these climate projections. Thank you.
Thank you, Sergio. Okay, so as Sergio said, now we have Danyang from Wageningen University, and she's going to show you the results of the environmental niche modeling that is including some more input variables into the modeling, and also looks into the environmental suitability for the sandflies. Please, Danyang, the floor is yours.
Thank you. Yeah, thank you very much, Suzana and Sergio. Good morning, everyone. My name is Danyang Wang. I'm from the Wageningen University in the Netherlands. We are the partner in both CLIMOS and the Planet4health projects.
Danyang, sorry, I see two. Can I just? I see two panels with you. I don't see the presentation in the big one.
I'll share one more time.
Okay.
Do you see my screen?
Yeah.
Properly?
Yeah. Yeah. Wonderful. Thank you.
Thank you. All right. I'm just to continue. So within both projects, we use different techniques to model the distributions of sandflies. Here I'm going to introduce or to talk about the environmental niche modeling, which, oh, I cannot switch screen. Yeah, okay. So within the CLIMOS project, we have the mandate to perform sandfly-borne diseases-related variable projections and modeling with environmental changes, and also to calculate effects of land covering use scenarios and distribution of sandfly species. So here we do not only look at the climate, but we also look at the land use. And later on, I will also show that there are more variables we take into account, at least to test and see their relevance, relative importance. Yeah. And also, because we're using the ecological modeling, so we do not only want to do the projections to the predict, but also try to understand their ecological niche. The environmental niche modeling, or ENM, is a word interchangeably used with the species distribution modeling. There are some nuance between the two, but they are often used interchangeably. Essentially, what they do is to link the observations of the studied species with their environmental conditions. And often they are spatially explicit, as you can see illustrated in the map. And the model can then build on the relationships and to see how the species use their environments, which parts is their niche. Here, what you see is like three-dimensional environmental conditions, but that can be higher dimensional, but it's a bit hard to picture here. And then based on this knowledge, the model can predict the habitat suitability for the studied species. Here is just a very simple overview of available SDMs. So there are different types. The most traditional one is the regressions, so like GLM, probably you're all aware of. But there are also distance-based modeling approach or neural network, which mimicking the human brain is quite hard to interpret. Or the classification and the regression trees, like what just now Sergio mentioned, decision trees, random forest, SGBoost are also part of this type of model architecture. And we also have Maxent entropy, and Maxent is the one which I use for the CLIMOS project. In addition, there's also Bayesian-based statistics, like INLA, for example. And then the second column shows you the models, which is focusing on the single species, but there are also joint species modeling, which is the third column to the right, so the column to the right. So there, they do not only use the knowledge about the species and their environment, but they also try to build down the relationship between different species and also use that knowledge to understand and to predict the species distributions. I believe the joint species distribution is also used in the Planet4health. All right. So from now, I'm going to talk about this study we have published recently, understanding and predicting the geographic distributions of flat-bottom and sandflies in and around Europe. And this paper is about long-term predictions and understanding, but actually we are using the similar techniques also for the short-term forecast. So the data and the process. The response variable of our model is the sandfly observations. So they come from the CLIMOS partners, mostly their historical data. But for the short term, we also use the CLIMOS collections in 2023 and 24. And part of those historical data are also from EDE Next project. Then we supplement those observations with the literature data which we could find. The predictor variables here are from open access data. So CHILSAP supplied us with bioclimatic variables. Land use variables are from Land Use Harmonization 2. Lithology variables are from literature. And we also have biodiversity indices and human population densities. So in total, we have 196 variables. So we test their relative importance for the species, and then also select the models. So I will talk a little bit later. As just now, Sergio mentioned, the trapping of the sandflies is rather biased, both spatially and temporally, because people normally go into the field to put a trap if they think there's possibility they can catch the sandflies. So they also often go in the season when sandflies are active instead of in the winter. So there is a bias. So in order to correct for that bias, we applied a different type of approach, that is environmental filtering. That means we look at the environmental conditions, considering all the predictor variables here mentioned, and if there are more points available in a single unique condition, then we just randomly select one for the model training and testing. Specifically for the Maxent model, we need to randomly sample background points. So a little bit similar as what Sergio just mentioned, like they have sampled in the boreal forest, boreal areas, there's a 0 points, but here its difference is that the background points in the Maxent basically says that the probability when to observe a species is about 50. So 50-50, it can be observed, or it can also not be observed. So that is the background point. Then we group the predictor variables into current conditions and future conditions. Not all the predictor variables we use have future predictions. Only the bioclimatic and land use variables have projections into the future, and the ecology variables are quite stable for the time scale in our study, so they will stay the same. Then we combine both data sets to have the training and the test data sets. Although I split it here too, just the one test and train, but actually we're doing the cross validation. Then we use the train data sets for the model fitting and to create models, and use the test data sets to evaluate all those models and produce performance metrics. Then we also found a way to compute the effect size, which is help us to understand the relationships. So Maxent model is not linear. So they have, for each variable, they have 5 features. So they have linear, but they also have hinge, threshold, etc. But we could figure out a way to calculate their effect size. And that is important for us to understand them ecologically. So I will show also the result later on about the response curve. Then with the metrics and the model and the effect size, we could select the model, because as I said, I had quite near 200 predictor variables. So we have pretty a lot models. So there we use those metrics to select them for model for explanation and the best model for prediction. And the predictive model, we use them to predict the habitat suitability for now and for in the future. Then by overlaying the maps of the different periods, we could get the shift of their suitable habitats. Here are some results for the long-term projections. Here we basically show the habitat suitabilities for the 12 studied species under the current situations. The colors show the probability of occurrence, and we also put the red dots there, basically the observations we have. So that's the places we have trapped the sandflies. This is the overlay of 5 vector species of the Leishmania infantum, and to overlay their map and see how diverse they are in different regions. And in map A, that is situation for now. So the lighter the color, more species present in, or suppose, so the habitat are suitable for more species in the same place. So in the map A, it is situation for now. And from B, C, D is getting more into the future. For the B is 2030 to 50. and then C is 2060 to 80, and D is the end of the century. So we're showing basically the same pattern as you saw with Sergio's work. We see they are moving northwards, eastwards. And this is also a presentation of the risk of the hazard, so vector hazard. This is more a quantitative way of presenting the same pattern we saw. So you can look at the two boxes to the right. Basically about 12% of the area in our study region, the places were not suitable for the study species now, but they will become suitable in the future. Well, the areas where now they are suitable for the sandflies, but will become not suitable, basically neglectable. So it's basically telling us the same message. The habitats, so the Europe become more and more suitable for those vector species. Okay, this is my last slide. This is basically the response curves of two species that I show here. So the top one is Phlebotomus pernicius, and the bottom one is Ariaceae. These two species occur sympatrically. That means they occur in the same region. They occur both in Iberia and southeast France, and pernicius is a little bit more further to France, but they occur in the same region. So there is a question like why they can occur in the same place, and so they should compete for the same resource. So there must be some type of kind of partitioning of their environmental niche. And indeed, that's the case. So the top graph is showing the maximum temperature in December for pernicius, and the bottom graph shows the climate moisture index in June. And these two environmental variables are very highly negatively correlated to each other. So here you see that the two species basically have the similar niche for their predictors respectively, but these two predictors are negatively correlated. So they are indeed partition their environmental niche. The other thing is that you see the blue lines, that's are the conditions available in the landscape, the higher, so this is density curve, the peak basically showing more areas are available. So for have that condition, so, and then the red curve is the niche of the species. So you do see that if you look at the pernicius, the above picture, pernicius have the right peak, so they are really are showing up where the niche is available, but you have the left peak as well. So they also have their preferred niche. So it's not just opportunistic when there is available condition, they occur there, but they do have their preferred niche. And this situation is more pronounced in the Ariaceae the figure. So they are like really showing, the two peaks are like in between of the two blue line peaks. So they have really their environmental niche. And you see the pernicius have the wider the band. So that's also kind of explain why in the landscape they are more abundant, or they are more, the range is bigger than the areas. Yeah, that's my presentation. Thank you very much.
Thank you so much, Danyang. Okay, so that was it from us. We're going to go for the another set of results, and this is the set of results for the Iberian Peninsula. Thank you.
Yes. So do you see my screen?
Yes.
Okay. So hi everyone again. In this presentation, I'm going to introduce our short range forecasting system for Sandfly presence in the Iberian Peninsula. as far as I know, this is the first time that an operational short-term prediction service for Sandflies is being implemented. So the goal is to move from research and modeling to a practical forecasting tool that can support real world risk assessment, surveillance, and decision making. So the main objectives of this approach are first to develop a short-range forecast of Sandfly presence with weekly predictions. Second, to apply models that can capture intra-annual variability, meaning certain climate-driven fluctuations within the season. And third, to support near real-time risk assessment through climate-informed predictive modeling. As I said during the climate projections presentation, first I'm going to talk about the data that we use to develop these models. So in this study, we work only in the Iberian Peninsula for this presentation and this use case. So our target dataset is the Sandfly dataset, which we use as the target variable. We group in this case we group the data by Leishmania type, focused in Leishmanian phantom, and we aggregate the species Tobi, Perfilieri, Major, Perniciosus, and Ariasi. And the temporal resolution is weekly because our forecasts are weekly. As in the previous approach, we also combine the data by sex, and then as in every machine learning problem, we harmonize the species name, clean the data, remove anomalies and missing values, and finally we obtain a clean and structured dataset ready for modeling Sandfly seasonality and occurrence. For the predictors, we use climate variables from ERA5 land reanalysis, data produced by Copernicus at a weekly resolution. We know that microclimate is important for Sandfly activity, but the data we have available are climate reanalysis data. In the same way that the weather services don't provide forecast for individual streets, our system is designed to provide predictions at municipal scale, not at micro local level. This allows us to build a realistic and operational forecasting service that can be applied consistent across the different regions, in this case in the Iberian Peninsula. The approach that we follow is the same, but the objective change a bit. So the objective of this machine learning models is to predict the presence or absence of Sandflies using climate related features, and to estimate the probability of finding Sandflies at a specific location and a specific time. So we start with the decision trees as a simple and interpretable model, which works well with the small data sets and allows us to understand how the model uses these variables. Because one of the good things of the decision trees is you can see how is the behavior of the tree. You can see how is the split of each box. Maybe if you check this schema, you can see that, for example, temperatures, the climate index based on days with the temperature above 35 degrees cut the tree, and then the algorithm learns that okay, there is no Sandflies above this threshold. So that's useful at the beginning to see how is the behavior of the different features. And we also use more robust and efficient models such as random forest or XGBoost, as I mentioned before, which provide us a more regularization, handle non-linear relationships, and reduce the overfitting, especially in small data sets. And here we can see the workflow of the short range forecasting system. So the target data are Sandfly occurrence from 2009 to 2023 at weekly resolution and aggregated by species and sex. The features are climate index derived from Era 5 land data, including temperatures extreme, precipitation, wind, soil moisture, and humidity variables. After pre-processing, cleaning, aggregation, and lag generation, we apply two model strategy. This modeling framework follows a data-driven approach. I mean, the models learn patterns directly from the data using the climate variables and observe Sandfly presence data. We include expert knowledge to guide the feature selection and model design, but the core of the system is data driving. When we say data driving, we mean that the model learns directly from the data instead of following fixed rules defined in advance by, I don't know, by me, by an expert, or by other system. So as I mentioned before, we have two models. The first model predicts when the season starts and when the season ends. And the second model is applied during the season and focus on predicting presence and absence at weekly scale. And by combining these two models, we obtain probability maps and time series for short range forecasting. For simplicity, I mean, to see some results, we show the deterministic results in the features, but the model itself is probabilistic. What we actually generate are probabilities of presence, which are then translated into forecast and risk levels for operational use. So the first model is the decision model. Okay, its goal is to predict the beginning of the season and the end of the Sandfly season. It captures interannual variability in season timing and doesn't predict activity during the winter months, which is consistent with published ecological literature. This figure shows the seasonal variation for allocation in Murcia, in the south of Spain. If we pay attention, if we check the figure on the x-axis, we have different years, and on the y-axis we have the day of the year, and we find three different points: the green points, the blue points, and the red points. The green points indicate the predicted start of the season, and the red points indicate the predicted end of the season. And we observe that the season usually starts around March or April and ends around October or early November. This is clear interannual variability, but no predicted activity during the winter months, which is good news. This shows that the season model captures realistic seasonal dynamics. The model also shows temporal and spatial variability, meaning that the season doesn't start and end at the same time everywhere. This model provides a stable seasonal structure, but by itself is not enough to explain the absence during the season. So here we can find a location when we apply the second model. The second model is in season. We apply the model between the green points and the red points. This model focus on short-term variability within the season. We know that the general climate conditions explain why there are more or fewer sandflies in different regions, but the recent events, the events that happened maybe last week, explain change in abundance from one week to the next. Short-term events such as extreme heat, heavy rainfall, or sudden change in humidity are the factors that drive weekly fluctuations in sandfly presence. So this model is a more expert guide and use only short-term lags. For example, in the season model, we use a 6-month lag, but for this second model, we just use 1 week lag instead of long historical lags. So its goal is to explain why even during the season, we sometimes observe absence. And these absences are often linked to as I mentioned, to temperatures above ecological threshold or extreme precipitation events. This model identified the most important short-term drivers of presence and absence. And here we see the spatial predictions over the Iberian Peninsula. I just put for years because if I put more panels, we don't see too much information. So this is the prediction over the Iberian Peninsula from 2019 to 2023, and we check these panels. We check these figures. The season model first define when the season starts and ends, and then the second model refines the predictions during the season. We observe that the highest probabilities are consistently located in the southern of Spain, while northern regions show lower probabilities. However, depending on the year and the short-term climate conditions, some locations outside the core areas can temporarily show suitable conditions. This shows that the model captures both large-scale patterns and local term variability. And as I mentioned at the beginning, when I started to show you the results, these models are probabilistic. So this figure shows the probabilistic results of the model, of both models, where predictions are expressed as probabilities. We can find more solutions, and maybe it could help us to the decision making. What we see here is a clear in the plot below, a clear unimodal seasonal structure with a defined beginning and end of the season, which is consistent with the ecology of the species that we are modeling in this region, in the Iberian Peninsula. However, we also know from ecological studies that not all species follow unimodal seasonal distribution. Some species show bimodal patterns with 2 activity peaks within the same year. A clear example is Tob in Israel, where bimodal seasonal distribution have been reported. This means that the modeling framework is flexible and can represent different decisional structures depending on the species and the ecological context. In this slide, we compare two locations, one in Andalusia, the figure above, and other one in Basque Country in the north of Spain. The upper plot shows higher probabilities, while the lower plot shows much lower probabilities. This reflects a strong spatial contrast in suitability. The blue line represents the decisional model, which defines the baseline temporal structure. And the red line is the combined model output, where the second model refines the prediction by accounting for absence patterns driven by short-term climate conditions. This two-step modeling strategy reduces probability overestimation and improves forecast realism. The seasonal model provides a structure, and the second model adds ecological knowledge by reducing probabilities when conditions are not suitable. This allows the model to produce more real and operational short range forecast. And that's all for this presentation for the short range forecast approach. And thank you so much. And I don't know if we have time for questions. I'm really happy to answer you.
Well, I think that finalizes our webinar. So from my side, I would like to thank you, everybody who joined us, and especially our speakers, Sergio, Danyang, Yoni, and Suzana. You were amazing, and Ivana for all the support. Nothing left to say, just keep an eye on our social media, especially LinkedIn and websites, because we will be posting the results of this webinar and the recording as well for you to take a look at it. And we will be having another webinar about the early warning system and how all this modeling and all this data, it's used for you to be like able to visualize it and use it and play with it. So yes, just keep an eye on it, and all the results and publications will come from that. I'm not sure, Suzana, you want to say anything else?
No, I think that's it. Thank you for being here with us for an hour and a half. And I just want to reiterate something that Danyang already said, that I mean, we as a modelers are absolutely supportive. And if you need our support, we are here for anyone who is doing any sort of Sandfly surveillance and collection of the data, or anyone who is doing the innovations in the ways how the surveillance is being done, because otherwise we cannot do anything without the wonderful surveillance job that is being done. Thank you so much.
Thank you all. Bye-bye.
Thank you. Bye-bye.
Bye-bye. Have a good weekend.
You too.